Ha, kids. All right. This little installment of general overview video is going to be about standing waves and resonance. Okay. First, let's talk about resonance. Make sure you guys understand it. So resonance. Okay. The key with resonance, you have two objects. Object A forces object B to vibrate at object B's natural frequency. Okay. That's resonance. Okay. When object A forces object B to vibrate at B's natural frequency, the amplitude will get bigger. Resonance. Okay. Examples of that: pushing somebody on a swing. If you push them at just the right frequency, you can make them go higher and higher and higher. Getting a wine glass to sing. There are lots and lots of examples, but resonance. Okay. That I'm not going to spend lots of time on that, but because one of the biggest applications of resonance is this idea of a standing wave and what happens with the standing wave. So let's talk a little bit about that. So if I have something like this. So let's say I have these identical, they're supposed to be identical waves. And they're moving towards each other. As these waves pass through, you're going to get what's called a standing wave. Okay? So as they pass through, you're going to get, when this goes through this, destructive interference, and then later on, this is going to be on top of this. See it? And while this is on top of this is on top of this, which means you're going to get constructive interference, and then you're going to get destructive, and then constructive, and then destructive, and then constructive, and then destructive. And then what you actually get as they're passing through is you get this, wave pulse. Okay, that moves back and forth. Okay, so like this is going back and forth, and it's called a standing wave. Why? Because it looks like it's standing still. It seems like it's not actually traveling along anymore, but in reality, it's made from, this is a special interference pattern that's made from waves moving this way and identical waves moving this way. Okay, there you go. Okay, these waves do have to be at the natural frequency of the medium or a multiple of the natural frequency, as we're going to talk about a little bit more in just a second. Remember a couple important points. Okay, those are my nodes. Easy to remember. No movement. Node has no movement. Haha. So that means you're always getting destructive interference there. And then this point here, this point right there, this point going back and forth. The part where you have lots of movement, that would be, you kind of have like anti-node movement. So you have an anti-node, and that's going to be where you have constructive interference occurring. Okay, so that's kind of the basics with standing waves. But let me show you guys how you're going to solve problems, because if you're watching this video, chances are you are probably struggling with that. Okay, so if there's a question that says something like, you have an open tube, you have a string that is at the second harmonic, or whatever it is, those type of questions, figure out the speed, figure out the length, figure out whatever. Okay, here's always the first thing you do. You do what you always do in physics, which is, that's right, draw a picture. Okay, so what we're going to do is we're going to draw a generic standing wave. Okay, so if I draw my generic standing wave, it looks something like, this. Okay, there's my generic standing wave. Then it all depends, guys, on your end conditions. Okay, so like let's say, okay, I'll first go through with you guys if you have two fixed ends. Okay, when would you have this? A string, okay? That a string kind of needs to be fixed in place on both sides. So like a string would be a great example of this, So if you have two fixed ends, well, what would be the natural frequency? Well, if it's fixed, that means there has to be a node at each end. Okay, which means, or if you want, you're going to get destructive interference occurring at each end. Well, if I wanted to show this, the first time that could happen, that would be at the natural frequency. So the first time that could happen would be, I'm going to go node to node. There you go, node to node. So if I had the first time, if I draw it, okay, if you look, that's what my picture would look like. If I call this distance L, okay. then I would have how many wavelengths from there to there? Oh yeah, that's a half a wavelength because there's one. Okay, so then I would have a half a wavelength equals L, and then my wavelength would be equal to 2L. And then I could solve for stuff. Okay, if you wanted to, if I wanted to do V equals F lambda, remember V is constant. Okay, so this is like 2L, so I would end up with V equals, this would be the natural frequency. Okay, sometimes it's called V0, sometimes it's called V1, but I'll call it V1 for the natural frequency. And then this would be 2L, so I get F1 equals V over 2L. Okay? Like again, I'm just doing some algebra here. All right. I'm going to do my next one up here because I think I got some room. So if I wanted, that would be the fundamental, that would be at the natural frequency. If I wanted to do the next one, okay? So sometimes this is called, this would be like the first harmonic, then the second harmonic. If I want to do the next one though, okay? I want to go, again, node to node. So the second time I can go node to node would be node to node. That much. So my picture would look like this. Okay? If you do the same steps, you would say, all right, I have one wave equals L. All right, so wavelength equals L. I know V equals F2 times my wavelength. Is everybody still with me there? So I now get F2 equals V over my wavelength. Okay, if you look, okay, V has to be the same, right? Yeah, same medium. Okay, so that, but if you look, well, how is this F going to compare to this one? Well, if you look, this F is, sorry, this is an L. Okay, this one is 2 times bigger than that. Okay, if I wanted to do it again, you know, my third time it would be here, first, second, third. That means that same length, I now have to fit, you know, a picture that looks like this. That would be 3/2 waves equals L, so L equals 2/3 this. V equals F times 2/3 this. So this would be like my F3, and then, yeah, you can still see. So that means F3 equals 3V over 2L. Hey, look, how does this compare to this? Oh, this frequency is 3 times bigger. So, hey, there's my pattern. That's how that works out. Okay, that would be 2 fixed ends. If I do 2 free ends, let's do the same process. If I was to do that same process, okay. All right, so let's do that. Okay, free end. That means each side has to be an antinode. Antinode, antinode. That's the first time it could happen. So my fundamental or my natural frequency is going to look like this. So I have a half a wave equals this, equals 2L. Same difference is just like I did. So I get V. So I get F equals V over 2L. Now it's the same equation, but I want to make sure you guys understand why it's the same equation. Don't memorize, understand, okay? The second time it could happen. First time, boom, boom, natural frequency. Second time, boom, boom. So then that's what my picture looks like. And I would say I have 1, okay? And then again, I'm going to get, you know, if I set it up, over L. So that means this one would have to be twice as big again, and then the next one's going to be 3 times as big. So hopefully that makes sense. So now let's do the one where you have 1 fixed, 1 free. Well, I should probably mention, guys, free to free would be an open-ended tube. Okay, so if it's open on both sides. Let's give you an example of a musical instrument that is like this. A trumpet would be like that. A clarinet, a recorder. If you did the lab where you blow over the top, so you have like a pan flute, open to open. Okay, that would be this. If we're doing fixed to free, This would be a closed tube. And some of you guys are like, oh, a closed tube, it has to be fixed on both sides. Yeah, right. Like, try to get a sound wave in a tube that's closed on both sides. That's not going to happen. This would be a trumpet. Fixed to free would be a trumpet with a muffle on the end. This would be, a pan flute where you put your hand over the top. Or when we did the lab where we covered one at one of the ends. Okay? But if it's fixed to free, node to antinode. So if you look, node, antinode. So that's the first time it could happen. How many waves is that? Oh, that would be a fourth of a wave. So this equals 4L. V equals F times 4L. F1 equals V over 4L. Okay, again, just same steps as we're doing. Second time with this one. Okay, if you look. Fixed to free, first one. Fixed to free, second one. So if I draw it, okay, so that means I have 3/4 of a wave equals L. This equals 4/3 this. V equals F times 4/3 this. Hopefully you can see that. So I get frequency equals 3V over 4L. Hey, look. There's the same thing. So that means, and a lot of times this is actually called the third harmonic because there really isn't a second harmonic because I'm going up to 3 times. Okay, but the second time that you would get a standing wave would be 3 times that first frequency. If I do the next one, fixed, first, second, third. Okay. So that's how much is inside there. How much is that? That would be 5/4 of a wave equals L. Go through the whole process, and the fifth harmonic, okay, you would get 5V over 4L. Oh, look, it's 5 times as big. And yeah, so, but my key that I'm trying to get across to you guys, okay, don't memorize. Draw your picture. Figure it out. It's not that hard. Bye, kids.